Today we're starting Unit 6, and we're going to be on Section 6.3, which is dealing with exponential functions. Now, up to this point, every single function that we have dealt with has been a linear function, meaning when we graph it, we get a line. Well, with exponential functions, we don't get a line. We get a curve. So let's take a look at what the definition of an exponential function is and then how we use it. So we have a value of a, which is going to be a number, and a value of b, which is going to be a number. A cannot be 0. It can be negative, it can be positive, but it cannot be 0. B has to be a number bigger than 0, so it has to be a positive number. It can be a fraction, it can be a decimal, but it can't be negative, and it can't be 0. This, y equals a times b raised to the value of x, that is our exponential function. That is our general form. Now please understand that there is multiplication happening between that value of a and that value of b, and only the value of b is being raised to the exponent of x. Okay? This is why it's called exponential, because we have the variable as the exponent. So let's talk about the difference between what a represents and what b represents. A is what we call the initial value. It's our starting place. We have questions that might deal with population, whether they increase or whether they decrease. That starting population would be our value of a. Similarly, we could have, like, we're investing money into a bank account or into a stock market, and that value that we're putting into it, that is our value of a. Now, one of the things that we have to remember with this initial value is that it is the y value when x is equal to 0. And another word that we've used for that in the past is our y-intercept. So basically, we are looking for that y-intercept as that value of a. Right? So if we're given a graph, we want to find that y-intercept. That tells us what our a is. Now our value of b, this is what we call the change factor. And what this is this is how our y values change from one to the next to the next. And the important thing about this is that it's whatever number we are going to multiply each time to get our next y value. Not add, not subtract, not divide, but multiply. All right, so let's use this information, and we're going to work on a couple of these problems and write the functions together. So if we look at number 1, first of all, I want to find my a, I want to find my b. Now as I set up here, our a, our initial value, is when x is equal to 0. And if we look at this table, I don't have an x value of 0. I have 1, 2, 3, 4. I don't have 0, so we need to find it. We need to find when x is 0, what is y. Okay? And we're going to get to that in a minute. To find our b, we're looking at our y values and saying, how do I get from one value to the next, right? What number are we multiplying by? And we should be able to see, to get from 2 to 4, 4 to 8, 8 to 16, we are multiplying by 2 every time. So that tells us our value of b is 2. Now, to find our a, you see how we're looking one less than this first point that we have here. So instead of multiplying by 2, I'm going to do the opposite, and I'm going to divide by 2, or multiply by a half. And we'll get to that here later on. So if we divide by 2 to go backwards, that tells us our value of a is going to be 1. So now, once we have our a and we have our b, we can write our function. Right, as we have up here, we're doing f of x equals a times b to the x. Well, a is 1, b is 2 to the x. Now the only thing that we need to do different here is that when I multiply by 1, it doesn't change it. So I don't have to have that 1 out in front. So we have f of x equals 2 to the x as our final function. Okay? Now number 2, this is a good problem that you may see a bunch of different examples of, whether it's in your homework or whether it's on a test or a quiz. Word problems are great for exponentials. So let's look at what it says. A petri dish started with 5 bacteria and it doubled every day. Your equation should model the amount of bacteria y after each day x. Okay? So again, we need our A and we need our B. A, remember, is our starting amount. It's our initial amount. So it says started with 5 bacteria. That's our A. Then, how is it changing every day? It's doubling. Doubling means we're multiplying by 2, so our B is 2. So now we're going to use y and x. We have y equals, our A comes first, our B is in parentheses, and our x is in the exponent. All right, and number 3, and again, we're in our folder here. Number 3, we can see we have a graph. Now, one of the things we should notice about this is this graph, our values are getting lower and lower and lower, okay, instead of getting bigger and bigger and bigger. So what we have here, we were looking for A, we're looking for B. I told you at the beginning, our value of A is our y-intercept. So if we look at this graph, we can see the y-intercept is right up at 100. And now because these values are getting smaller and smaller and smaller, right? My next y value is over at 50, right? I started at 100, I got to 50. When we are getting smaller, our value of b has to be between 0 and 1, so it has to be a fraction. The easiest way in order to figure out what that fraction is, take the smaller number, divide it by the bigger number. So if I do 50 divided by 100 and I reduce, gives me 1/2 as my value of b. So now we have A, we have B, so we can write f of x is equal to 100 times 1/2 to the power of x. Now, one of the things that I want to make sure that you understand is that this 100 times 1/2 to the x is not the same as 50 to the power of x. This 5 times 2 to the x is not the same as 10 to the x. We cannot multiply those two values together. Okay, so please make sure that you just leave it written as this. And we're going to see that here in a little bit. Okay. All right, so let's go into our notes. Let's go into page 124 in our notes. And let's take a look at problem 1. And we're going to use Desmos here, or at least I'm going to use it in order to show you some of these graphs, and then we'll take a look at what we have. So if we look at number 1, it says identify the key features. We're going to talk about those in a minute. Of the function f of x equals b to the x for when b is 2 and b is 1/2. So we have two different functions that we're comparing here. We have f of x equals 2 to the x and f of x equals 1/2 to the x. Now when it says key features, there are 4 of them that we're going to consider. We have domain, we have range, we have the y-intercept, and we have a new term, which is called the asymptote. Okay? So those are the 4 things that we are going to consider, and I'm going to talk about what the asymptote here is in a minute. All right? So I'm going to go ahead, I'm going to pull Desmos up, and I'm going to graph this first equation. So I've got y equals 2 raised to the value of x. All right, and I'm going to zoom in here so that we can see it a little bit better. So what we can see is we can see this graph is a curve. Okay, we're no longer dealing with straight lines. We have a nice curve here. So there are a couple of things that we can find right away. We can find the y-intercept of those key features. So we can click on it and say, hey, the y-intercept is at 1. Awesome. Now let's talk about the other things, because a couple of them go hand in hand with each other. All right, let's talk about domain first. Now remember, domain is all of your x values. Well, if you remember from Unit 3, at the beginning of Unit 3, when we first talked about domain and range, we always looked, how does the graph kind of behave? Is it going all the way to the left? Is it going all the way to the right? Does it go on forever? And we can see, and it might be hard to see, but that's why I like the green here. If I just keep going to the left, this line is just going to keep on going and keep on going. So it's going to go to the left forever. And if we look to the right, you can see it's going up, but it's also ever so slightly moving over to the right. So even though it doesn't look like it's going right, it is going to go to the right forever. Okay? So we have a situation where the graph is going to the right forever, it's going to the left forever, and it's just a continuous function. And if we recall, we said that a function that is going continuously in both directions, left and right, the domain is going to be all real numbers. And this is going to be the case for every single exponential function. Every single exponential function that we do, our domain is going to be all real numbers. All right. Now, we want to look at our range and our asymptote. Now, let's talk about the asymptote first. This is a new term for us. And I want you to look at the graph in order to see what's going on. As we talked about, we have this curve here, and then, like I said, this line just kind of keeps going. And if I zoom out and keep going, do we see that this line is really never going down anymore? It's just staying flat and staying flat. So it's basically hovering right at this same spot. There's an imaginary line here. There's an imaginary boundary. And that imaginary line is the asymptote. Okay? And what we're going to look at is, where does it come down to? Where does it look like it's leveling off to? And for us, we're looking at our y values. We're looking at what y value is it coming down to, and we can see it's when our y value is at 0. We can see it's hovering and hovering close to 0. And it will actually never touch 0, and it will never cross 0. Okay? I can shift this graph up and push it down, doing our translations like we've done before, but for right now, it's coming to 0 and it's never actually touching it. All right, so our asymptote here, again, it's a horizontal line. Horizontal lines say y equals, and it's the number that we're at, 0. Now your range is always going to go hand in hand with your asymptote. Wherever your asymptote is, that's where your range is going to start, whether it's going up or whether it's going down. And if we look at this graph here, do we see how this entire graph is above that line? It's above that asymptote. When it's above, we're going to say y is greater than that same number, right? In our case, y is greater than 0. It's not equal to, because it never actually is equal to 0. It just barely misses it. Now, if it was less than, and by less than I mean the whole thing is underneath 0, that's when this whole thing is negative and everything flips down. So it's at 0, or it's just below 0, and then it keeps going down forever. Okay? But for our sake, everything is at 0, is above 0 here. Okay? Now, if we do the same thing, we're going to compare here. We're going to look at, again, our domain, range, y-intercept, and asymptote. For at y equals 1/2 to the x. So I'm going to turn this one off. I'm going to put the other one on. Y equals parentheses 1 divided by 2 raised to the value of x. And we can see that now, because it's 1/2, we're going down, we're decreasing. We can see that this graph is going down and to the right instead of up and to the right. And again, it's the same thing. Our domain, we already talked about it, it's going continuously in both directions. So our domain is still going to be all real numbers. If we look at our y-intercept, it's still at 1. If we look at our asymptote here, it's still at 0. Okay, it's just going in this direction, but it's still at y = 0. And our graph is still above that asymptote, so we can say the range is still y is greater than 0. So even though these two functions are different from each other, and we can see from the graph they look very different, right? One is increasing, the other one's decreasing, but all of those key features are the same. The y-intercept's the same, the domain's the same, the range is the same, and the asymptote is the same. Okay? All right. Let's keep going. All right, now number 2, I don't have all of it written here, but it tells us we have the function f of x equals 5 to the x. It says x is number of hours that it takes for a virus to spread to different computers, and it says y is the number of computers that that virus is infecting. And it says how long will it take the virus to spread. So we're going to use Desmos in order to do this, and it tells us, hey, at 50,000 computers, how long is that going to take? So it says y is equal to 50,000. What is x? That's what we're looking for. How long is it going to take? So let's use Desmos. Let's type in our original function of y equals 5 to the x. Okay, it's increasing, going to the right. And because we are looking for when y is equal to 50,000, I'm literally going to type that in a second equation. I'm going to type in y equals 50,000, and I'm going to zoom out here. And as I continue to zoom out, I can see that there is an intersection between these two graphs. And I'm going to find that intersection point. And it tells us right here at 50,000 computers, it's going to take 6.72 hours in order to do so. So the graph does all of this work for us. 6.72 hours. Okay? And again, Desmos can do this work for us. We just have to know how to use it. All right. Number 3, write an exponential function for each one. Again, we are looking for f of x equals a times b to the x. Remember, a is our initial when x is 0. So if we look at part A, we have x is 0. So the y value, that's our a. Now, we look for how does my y values change. Oops, this one. So how do my y values change? What do I have to multiply by? So to get from 3 to 12, I multiply by 4. 12 to 48, multiply by 4, right? So that is going to be our b. b is going to be positive 4. So we have our a of 3, we have our b of 4. So we can say our function, f of x, is equal to a, 3, times b, which is 4, to the x. Now if we look at b, again, I have x is 0, so I have my value of a, 2,187. 2,187. I'm just looking for my b. And we can see that our y values are getting smaller. 2,187 to 729 to 243 to 81 to 27. And remember, I talked about it. We just take the smaller number, divide it by the bigger number. right? So and it doesn't matter which two points I choose as long as they're right next to each other. So if I chose like 729 divided by 2187, that gives me 0.33 repeating. It's the same thing as if I did 27 over 81, it's still 0.33 repeating, and we just convert that into a fraction, which gives us 1/3. Okay, so we are multiplying by 1/3 every time. Okay, and that's our function. A is 2187, B is 1/3. All right, a couple more and then we'll be done. Flip your page over. Let's take a look at the tables, number 7 and number 8. So if we look at number 7, we do have an x value of 0, so we know our value of A is going to be 4. Then we can see our y values, or our f of x values, they are getting smaller. So that means we're multiplying by a fraction. So what number are we multiplying 4 by to get 2, 2 by to get 1? We're taking half of each of those values. So A is equal to 4, B is equal to 1/2. So our function is going to say f of x equals 4 times 1/2 to the value of x. And then our last one, again, we have an x value of 0, so A is equal to 3. We then look at our y values and say, how do we get to each one? 3 to 6, 6 to 12, 12 to 24, and so on. We are multiplying by 2, so that's going to be our b. So we have f of x is equal to a, which is 3, times our value of b, which is 2, raised to the x. And that's our basic level of understanding of exponential functions. Hopefully that helps when you work through your homework 6-3. If you have any questions, please reach out, and we will do the best in order to help you. Thanks.